Okay, let's go ahead and look at example 2. We have a block that has a mass of capital M and it hangs from a string. If the block is accelerating upward with an acceleration of A, what is the tension in the string? Okay, so the first thing we need to do is we need to go ahead and draw our motion diagram and our free body diagram. It says here that the block is accelerating upward. So what I'm going to do is I'm going to start out with my velocity vector being a half a centimeter long, then I'm going to go to a full centimeter, and then I'm going to go to 1.5 centimeters. Okay, so this indicates that I am increasing my velocity. Okay, and that means that my acceleration is also going to be directed upward. And again, this is called pale purple, which in my opinion looks pink. Okay, so now we're going to go ahead and draw our free body diagram. So what's physically touching the block? Okay, so let's look at the problem. We have a block hanging from a string that's accelerating upward. Okay, so what's physically touching the block? That's right, the string. And what's acting at a distance? The Earth, that's right. And are we in equilibrium? No, we're not. Okay, so what I'm going to do is I'm going to go ahead and draw my, sorry, wrong color. I'm going to draw my dot to indicate my object. I'm going to draw my tension going up, and I'm going to draw my weight going down. Let's see, I have this as being 2 centimeters and this is 1.5. I just need to make sure that the net force is directed upward. Okay, so this is the force on block by rope, and this is the force on block by earth. Okay, so now we're ready to apply Newton's laws to this problem to solve for the tension in the rope. In order to do that, we're going to start out with the sum of the forces equals ma. We're only working in the y direction, so we only need to write one equation. Remember, because forces are vector quantities, if we're going to use this equation, we have to make sure that we're only going either in the x direction or the y direction. Okay, so we can't add x's and y's together. Okay, so the next thing we're going to do is we're going to substitute all of the forces from our free body diagram into the summation. So we have force on block by rope plus force on block by earth, and that's equal to ma. Oops, let me make a capital M. Now, some of you may be thinking, wait a minute, Dr. H, why did you put a plus sign here? Isn't this going down? Yes, the force is going down, but notice I'm adding the vector. This vector sign tells me that this is going to have a magnitude and a direction inside of it. What does summation mean? It means we're adding them together. So we have to add the forces together. Now, once we've replaced the vector sign with magnitude and direction, that's when the negative falls into play. Okay, so are we accelerating? Are we in equilibrium? No, we are not in equilibrium. We have a net acceleration, and therefore we're going to leave the A there. And that tells me that I have applied Newton's first law, that I have looked at my diagrams, and I have made sure that I either have an acceleration or I don't. Okay, the next step is for us to substitute in magnitude and direction. So let's go ahead and do that now. I have force, oops, sorry, no vector sign there. I have F on block by rope J hat minus mgj hat. Notice that I'm replacing the force on block by earth with its formula, mg. Okay, notice the negative j hat is the direction. Okay, so when you substitute in the magnitude and direction, you're going to substitute in the formulas that you were given in the first page of your lecture. Okay, and this is equal to, now this is the part. Which direction is the acceleration going? If we look at our diagram, we can see that it's directed upward. Okay, so that tells me that I'm going to have MAJ hat. Okay, the next step is for us to cross out all of the unit vectors. And so when I cross out all the unit vectors, I then have a scalar equation. I'm going to go ahead and solve this for the magnitude of the tension. So I have force on block by rope is equal to MA plus MG. So the tension in the rope is going to be more than the weight of the block. Does that make sense? Yes, it does. If it weren't more than the weight of the block, it wouldn't accelerate upward, right? That downward force would have a greater magnitude and it would accelerate down. So we want this to be larger than the weight, and it is. Okay, so did it ask us for the magnitude of the tension, or did it ask us for the tension in the string? It says, what is the tension in the string? So now I have to give it a direction. So I'm going to rewrite my answer. See, this is the magnitude. So I'm going to write F on block by rope is equal to MA plus MG J hat. Notice I don't put a negative there because it's directed upward. Now again, some of you may be saying, wait a minute, could you just solve this equation for force on block by rope and just take this to the other side and then substitute? Yes, you can. Okay, but like I said before, I want to go through all of the steps that you are going to need to do for the more difficult problems. Okay, so when we get into those two-dimensional problems, that's where it gets a little sticky, and that's where you have to use X and Y direction. And so when we get to those problems where you need X and Y, we're going to have to worry about getting rid of those unit vectors because we can't add I hats and J hats together. Okay, we're going to box our answer. And there you go. That finishes the second example.